Hi there, my name is Ferriere, and I'm here to talk to you about my data mining Capstone project, part of the Coursera data mining specialization, offered by the University of Illinois at Urbana-Champaign. In this video, I'll give you a quick overview of the data mining problems we were asked to solve using Yelp restaurant reviews, going over the techniques I experimented with, my results, and how they can be generalized to other datasets. For the first assignment, the goal was to differentiate the topics of positive and negative reviews. To extract topics, I used the latent Dirichlet allocation model, or LDA. Applying the same model to all the reviews, only the positive ones or just the negative ones, I ended with the same major categories: type of cooking or food served, quality of service, and type of venue. The word distribution describing each topic, however, did change. To visualize these changes, I decided to experiment with word clouds, but encoding intra-topic ranking instead of term counts. I used the word distribution that describes the topic and gave the top term a weight of 20, and the least common one a weight of 1. Then, topics were paired between negative and positive reviews, and the corresponding word clouds were displayed side by side. In the example shown here, the green word cloud on the left is for positive reviews, while the red one on the right comes from negative reviews. The topic is the same, and as you would expect, the most common terms are identical: food and service. But you can easily see the differences in appreciation. On the left, there are words like amazing or excellent, friendly. On the right, what you see is a lot of negative words like horrible, terrible, and bad. To use the same technique with your own dataset, first extract topics, and once you've paired them across positive and negative reviews, look at how the word distribution of each topic changes. For a consumer electronic product review, common topics might be packaging, durability, ease of use, or customer support. Any business interested in understanding what customers like or dislike about their brand or products can benefit greatly from this improved level of detail. The objective of the second assignment was to find the best way to represent the cuisine using review text data, so that similar cuisines could be grouped together. Using term frequencies with TF-IDF weighting and Spearman correlation coefficients, I was able to extract meaningful groups of cuisines. To create clusters, I used average length hierarchical clustering with 9 clusters. To visualize similarities and the clusters, I used correlograms. Every cell in a correlogram represents the similarity of 2 cuisines. One only needs to follow the horizontal and vertical lines leading to a cell to identify which 2 cuisines it is comparing. The deeper the color, the stronger the similarity of the 2 cuisines. In the final correlogram shown on this slide, the clusters are marked as black squares. The image on the right is a zoomed version of the bottom right cluster in the correlogram, and as you can see, all 9 styles of Asian cuisine were correctly grouped into the same cluster. Here again, you can use this with your own dataset. For any online retailer that sells hundreds of thousands of products, being able to group products in meaningful categories is required to help online shoppers. It can be done from customer reviews, as we saw, but also from product descriptions. By varying the number of clusters, or clustering within clusters, you can also identify subcategories within categories. However, to really benefit from the type of hierarchical clustering I used here, you need to be prepared to experiment with different kinds of clustering algorithms and different similarity measures. You will also need to spend a bit of time fine-tuning for the best number of clusters. In the third week of the project, we were given a list of dish names, and armed with this list of seed terms, we were to mine additional dish names from restaurant reviews. For this task, I decided to experiment with a different vector space called Word2Vec. Word2Vec was developed by Google. Its input is a text corpus, and its output is a set of feature vectors for the words in that corpus. Features, such as the context of individual words. The purpose and usefulness of Word2Vec here is to group the terms with similar context together in vector space. Using cosine distance in Word2Vec vector space, I searched the entire corpus of Chinese restaurant reviews for terms similar to the ones in the original list. Using this technique, I was able to mine quite a few additional Chinese dishes. There were also a lot of cooking terms and ingredients, but it's not that surprising. With popular dishes named fried rice or sautéed green beans, other cooking terms are bound to be matched to them. Snap peas can be both an ingredient and an appetizer. What was a bit more surprising was that it also matched dishes from other cuisines, but those could easily be filtered out by forcing membership of a dish in a cuisine where the engram appears most often. To use this with your own dataset, the process is fairly simple. First, build a list of terms to be used as seeds, using whatever technique you want. Second, encode them and your corpus in word-to-vec vector space. Third, use a similarity measure to mine terms similar to the ones present in your master list. You can use those new terms to suggest related or additional products or services to the ones customers are already searching for on your website. You can also use those terms to improve search results by including hits for the additional terms as well, not just the ones the user typed. Linking terms, concepts, products, information is always a great way to promote surfing on your website. Tasks 4 and 5 were tackled together. Task 4 was about finding the best way to rank the dishes of a particular cuisine based on the reviews that mentioned those dishes. Task 5 was about ranking the restaurants that serve a specific dish based on the reviews that mentioned that dish. To rank popular dishes, I tried 4 different approaches, using term count, number of reviews, number of restaurants whose reviews mention a dish, and finally by sentiment. To compare and visualize the differences between the 4 ranking models, I experimented with slope graphs. Here's my first attempt at combining the 4 rankings in one slope graph. Dim sum is first by 3 rankings. For these rankings, it appears first and at the top. By restaurant mentions, where it is ranked 18th, you can see a huge dip to 18th position toward the bottom of the graph. So this slope graph certainly captures rank by position and order very well. This graph also captures similarity between rankings. The first 2 models resulted in almost identical rankings, and that is made visible by the many short, parallel slopes between the first 2 vertical axes. It also does a good job at emphasizing major changes in ranking with long, sharp slope lines, as we saw for dim sum. That being said, a large number of crossing slope lines can be overwhelming, so I tried a slightly different approach. Making the graph interactive, using a mouse hover to highlight one ranked item in a different light type and color, really improved readability. Also, keep in mind that these slope graphs were generated in R with ggplot2, not the greatest library when it comes to creating visually appealing designs. It is not D3JS. But with just a tiny bit of interactivity, visualizing changes in rank for a single item became very easy. So when should you use a multi-rank slope graph? Today, whenever you go to your website and want to compare items, listings, rentals, or products, you are presented with a drop-down box with an order by choice. It can be order by price, reviews, top selling, whatever. You then get a ranking in whatever dimension you selected. If you want to see how items rank according to another dimension, you must go back to that drop-down and get a new set of results. But the results of the previous ranking are no longer available. When you get to your third drop-down choice, good luck remembering how each item fared in the first ranking. This approach really constrains users in making a decision by relying on a single dimension. If you want to allow shoppers to use a more sophisticated decision-making process, and you actually have rankings along several dimensions, then combine them in a slope graph, or let the user choose which dimensions to include. For our last assignment, we were asked to train a classifier that could predict if restaurants would pass a public health inspection based on their Yelp reviews, as well as some additional information, such as type of cuisine, star rating, number of reviews, and restaurant location. For text features, I tried several combinations of unigram and bigram models. The final model, with text features, was a combination of TF-IDF-weighted unigrams and TF-weighted bigrams. To train classifiers on comparable features, I performed z-score normalization by subtracting the mean of each feature and dividing the result by the standard deviation from the mean. I also discarded low entropy features, that is, predictors with constant values or near zero variance. I split the original label data into 80% training and 20% testing partitions, and made sure to keep the original stratification for the outcome values. I did not create a separate validation set because I used tenfold cross-validation on the training set, meaning that for each fold, 10% of the training data was set aside for validation purposes. Because there was a major imbalance between positive and negative outcomes in the data, rather than relying on accuracy as a training objective, I used the F1 score instead, that is the harmonic mean of precision and recall. I trained 7 different classifiers, including XGBoost, GBM, KNN, SVM, random forests, and 2 naive Bayes classifiers. When using only non-text features, support vector machines on average perform slightly better. Adding text features, the random forest classifier was the best, but the improvement in F1 score over the non-text features classifier was only marginally better. To understand why, we can look at variable importance. According to the variable importance table on the left, the one for the SVM classifier, restaurants that failed the health inspection tests are characterized by a high number of reviews and the type of cuisine they serve, mainly Asian cuisine. They are also concentrated in 3 specific zip codes. Now, if you look at the variable importance table of the random forest classifier, the top predictor for a restaurant failing the inspection test is the presence of the word noodles in the reviews. Does it mean those restaurants serve somewhat contaminated noodles? I don't think so. If you look closely at the table, you can see again that the restaurants are located in 3 main areas, the same zip codes as the ones on the left. Chinese restaurants are again at the top, but Thai, Vietnamese, and Japanese restaurants have disappeared from the list. Well, not really. They've been replaced. The term noodles here is a substitute for the Thai, Vietnamese, and Japanese restaurants, where they are one of the most popular dishes. And that's what the random forest classifier, trained with text features, brilliantly captured. That's it. If you would like to learn more about me or my work, please don't hesitate to reach out on LinkedIn or via email. If you're a student who just enrolled in the data mining specialization and would like to know more about my experience with the Capstone, feel free to send me your questions, and good luck to you. Thank you for watching.